This video is about gravitational potential and gravitational potential energy, two terms which sound very similar but have different meanings which we need to be clear about. We're going to talk about how to calculate these quantities and how we can use the concept to calculate the energy required to move away from planets. So you might think I already know the equation for gravitational potential energy. It's just mg delta h. If you were asked a question at the moment and you were lifting a 3 kilogram mass by 3 meters in the lab where you're sitting, right, then you'd work out the change in energy is just mg delta h, so 3 kilograms times 9.81, the gravitational field strength on Earth, times 3 meters would give you 88 joules. Even if you had to carry something up a 3,000 meter high mountain, you could still probably reasonably validly use the same equation and get 88,000 joules. But if you tried to lift something 30,000 kilometers, right, then you would run into the problem. And the problem is the fact, of course, that G, right, although we say G is 9.81, that is the gravity, the strength of the gravitational field at the surface of the Earth, and that will change. So the problem with using mg delta h is that it's a perfectly reasonable approximation if we consider G to be, if delta h is a fairly small distance and we can consider G to be a constant, but G is not a constant if we use a big distance. So to look at that graphically, if we were, say, at 6,400 kilometers away from the centre of the Earth at the surface, we were even to go up 80 kilometers, or almost up to the edge of space. This is the shape of the strength of the gravitational field, right, 9.81 minus because it's down towards the centre of the Earth and we're going up. And it hasn't really changed much by 6,480, so it would be a reasonable approximation. We'd be doing this rectangle, and that would be a pretty good approximation to what we actually want, which is the area under this line. But of course, if we were going a big distance, if we're talking about launching things into space, for example, that wouldn't be a good approximation because this part of the graph would only be a little bit of this big graph, and this big graph clearly has not got a constant gravitational field. Right, this would not be a very good approximation to the area we want, which is something like this blue area here. Okay, so we're going to look at these terms defining gravitational potential. A very precise term. We have to be careful of a few details in here. So the gravitational potential at a point is the energy required to move a point unit mass from infinity to that position. Quite a lot to think about in here. First of all, we are moving a point unit mass, so this is per kilogram. It only has to be a point mass because that way the gravitational field is one value at that particular point. And we're coming from infinity. So you might think it sounds like quite a strange definition because the energy required to move from infinity to a position will be a negative number, because of course it takes energy to move things further away from the Earth, not to move things towards them. But there are reasons that it's done like that, which we'll come back to in a minute. What that means, of course, is that this is always a negative number, because in fact energy is always released in gravitational potential. And the units for gravitational potential are joules per kilogram because it's per unit mass. Okay, so we need the distinction between gravitational potential, which is the energy per kilogram, and gravitational potential energy, which is the actual energy. So to get from one to the other, all you have to do is to multiply the gravitational potential by the mass to find the gravitational potential energy. Okay, there is a little bit of calculus on this, so a third sort of way of looking at it, if you like. Remember, work equals force times distance. Well, potential energy is mg delta h is really the same equation because the force that you're using to lift something is mg, and delta h is the distance you're moving it. We can rewrite this now, if we've got a variable force, as the integral of f ds. If f is a constant, then that's just fs. But if f is variable, which we now know it is, we know f is gmm over r squared. So it's the integral of gmm over r squared dr, okay, with respect to the distance away from the planet or the star, and the integral of r to the minus 2 is minus r to the minus 1, So you end up with this equation. I've missed out a plus c because we're going to put some limits in it in a minute. Okay, and our limits, well, if you remember the definition, what we're doing is we're coming from infinity to that point. So our limits are infinity and r, and the integral of GMM over r squared with respect to r between infinity and r is minus GMM over r, because the infinity on the bottom becomes a 0. Okay, whereas if we'd done it from r equals 0, which you might imagine would be a better answer, we're going to get GMM over 0, and mathematically we're going to be going into a bit of a bad place. This is the equation for the gravitational potential energy of an object at some distance r from the centre of an object of mass m, when I've got the object that I'm measuring the potential energy of with a mass of little m. And the potential is energy per kilogram, so we just divide that by the mass of the object, which is minus GM over r. Okay, the symbol confuses people here sometimes for two reasons. So V looks a bit like voltage. Well, there is a reason it looks like voltage, because this is gravitational potential is the energy per kilogram, whereas if it's V for voltage, that would be the energy per coulomb. Okay, so it's the same kind of concept, energy per unit of the thing that we're measuring the field on. The other thing for people that get a bit desperate in exams sometimes is they're looking for the velocity of something going around a planet, and they see this equation and get excited, but this has got nothing to do with V for velocity. This is a capital V, not a small v, so be careful with your handwriting so that you don't get confused by that. Okay, a few questions. So calculate the potential energy of a 10 kilogram mass at the surface of the Earth. Okay, so we just do Gm1, m2, or big, sometimes we use big M, little m, sometimes we use m1, m2, doesn't really matter, okay, over r, put the numbers in, that gives you minus 6.23 times 10 to the 8 joules. Okay, what that's telling you is it would take 6.23 times 10 to the 8 joules to move that object from the surface of the Earth to infinity, or that amount of energy would be released if the object fell from infinity to the surface of the Earth. We could therefore calculate the speed of the object that would hit the Earth if it fell from infinity, because we'd say its kinetic energy would be that amount of energy. For God's sake. Its kinetic energy would be that amount. So we could rearrange that to get the V, and it tells you that an object hitting the Earth from infinity would hit it at about 11 kilometers per second, or if you wanted to throw something up, you'd have to throw it at 11 kilometers per second to make it get to infinity, if we're ignoring things like air resistance and the fact that everything's already moving and things. If we wanted to calculate the potential energy required to move a 100 kilogram satellite for an orbit of radius 7,000 kilometers to 42,000 kilometers, so this is the kind of problem that people have when they've launched a satellite into space and it's 600 kilometers above the ground and they want to move it to a geostationary orbit at something like 42,000 kilometers from the centre of the Earth. Right, then we just simply work out the two gravitational potentials and work out the difference between them. So GMM over R1 for the first radius and the second radius, and we find it takes 4.75 gigajoules of energy to make that happen. Okay, the third question, we're just going to click on to a graphical representation of this, so I'll just show you that. So this is equipotentials around the Earth, which is an important idea. So here's our graph. Now this graph, remember, is not the same as the one at the start of this video. This is the gravitational potential in megajoules per kilogram. Here we are at the surface of the Earth at about minus 62. If you wanted to draw the equipotentials around the world, these are points where anywhere on that point has the same potential energy. They're a bit like contour lines, if you like, in space. So here's our minus 60 megajoule per kilogram line. It's that far away. Any point that far away from the Earth will be minus 60. Here's our minus 50, just read them off the graph. But the important thing is to look what's happening to the separations of these equipotentials. Okay, they're getting bigger and bigger and bigger. So if we draw them out, anywhere along this point will have the same potential energy. Therefore, if you're a satellite in orbit going around here, it doesn't take any energy to keep you moving because you're going round this equipotential, this contour line if you like, in space. The spaces between them are getting bigger, as you'll notice. For example, here's our minus 61. If we go to minus 30, we're twice as far away from the centre of the Earth. Okay, at minus 30, we're twice as far away from the centre of the Earth. So this distance from here to here is the same as this distance from here to the centre of the Earth, and so on. By the time we got to minus 15, we'd be double this distance away. Okay, so you'll know what you can tell from that is that by the time you get to here, for example, from the surface of the Earth, you've already used up half the energy that you need to get to infinity. And it's really the first part of getting away from the surface of the Earth, which is the hard part of the journey.